Welcome back to another video in our course in stochastic processes. We learned about martingale convergence last time, so we had some results on almost true and LP convergence of martingales. And today we will augment this with some more results, which are corollaries and applications. Let's see. So this is our second video on martingale convergence, and let me start by recalling what we did last time. Apart from some typos here, so we have a filtration. We are usually always dealing with the natural numbers as the index set, and let's assume we have a submartingale. We had here 3 convergence results. So the first is dealing with almost true convergence. Sorry, that's an A here. And that tells you have to check one thing, which is the supremum of this expectation here is finite. And then you already know that there is almost true convergence to some L1 random variable. The second and the third deal with not only almost true convergence, but also with L1 or LP convergence. And so the second here is really central. If you also have that X is uniformly integrable, okay, then this here is automatic, such that we have almost true convergence anyway. But we also have convergence here in L1. And that also means that you can augment the submartingale by the point infinity. And, well, you have that this is also a submartingale, which is a very nice property. Okay, and the third, that's not so exciting anymore, because you basically apply the second result to x to the power of p. And then you get the third result. Okay, so these were the 3 things. And let me start with one application before I come to some more stuff, which is the following. So ST is a product here, and all x's here are non-negative. Then already we know that ST converges almost surely to S infinity. And as we learned, it's important to see when is the martingale here uniformly integrable. And it's uniformly integrable if and only if this thing here is positive. And AT is the expectation of the square root of xt, which is a bit a funny thing to look at. So, yeah, let me just use here my proof. First of all, of course, WT, which is the product not over XS, but over square root XS divided by AS, that's a martingale, okay? Because all these numerals have expectation 1 by construction. And therefore, it's a non-negative martingale, as we had last time. We had this thing here, martingale convergence for positive supermartingales. A martingale is a supermartingale, it's positive here, and it converges almost surely. Okay, that's the basic thing here. Now we have to prove 2 directions. So first of all, the almost true convergence here is immediate by the same argument. It's a non-negative martingale. So the ST by itself is a non-negative martingale. So from right to left. So I'm claiming if this here holds, then ST is uniformly integrable. AT square, okay, that's this square here, by some Cauchy-Schwarz inequality or something, and that's less or equal than 1. And the expectation of WT square, I can show it's finite. Why is it finite? Okay, WT square, I have the square of the square root, which is XS itself, and AS square is this thing here. The expectation of XS is 1. Okay, that's easy. Or they're independent, so I can make that the expectation of the product is the product of the expectations. And in the denominator, I have this product here. And as we're in the direction from right to left, that product is non-negative. It's not zero. Sorry, it's not zero, which means that this here is finite. So we find that WT is an L2 bounded martingale, so it's uniformly integrable. And by this, we see that the expectation of WT square converges to the expectation of W infinity square. And from this, because WT square is almost the same as ST apart from the denominator, we find that the expectation of ST converges to the corresponding expectation of S infinity. And therefore, we have almost, we do not only have almost true convergence, but we also have L1 convergence of the ST here. And by this, we see that ST must be uniformly integrable. So for the other direction, let's assume that that product here goes to 0. And ST converges almost surely. And the only possibility is that ST converges to 0 in this case. Now, if ST would be uniformly integrable, we would have that S infinity converges, the expectation converges to 0. If it would be uniformly integrable, L1 convergence would follow, but then 0 would be 1, which is a contradiction, so it cannot be uniformly integrable. And we have shown this nice result. Okay, let's go on with convergence of conditional expectations. Here I claim that, so I have some x here, and the conditional expectation of x given ft converges to the conditional expectation of x given f infinity, which is the sigma algebra generated by all the ft's. Why is that? So I can consider the martingale expectation of x given ft, and t goes 0, 1, 2, and so on. That's a martingale, as you can simply read in our first examples of martingales, or just prove it by yourself by the tower property of the conditional expectation. That's a martingale. It's also uniformly integrable. As I recalled also last time, we had a result which guarantees this. So there must be some x infinity such that this conditional expectation converges almost surely and in L1 to x infinity. So that's from uniform integrability of this martingale here, because we know that all conditional expectations of an integrable random variable, that's an uniformly integrable random variable. And now write the following. I take this x infinity and I integrate it over some set A, and A is in Fs, say. X infinity is the almost sure and also L1 limit of the expectation of x given ft. So I can say that's the limit of this thing here. this here over this set here. By definition, since fs is subset of ft for t large, that must be the same as the expectation of x on the set A. So I have this thing here, and now I can let s go to infinity. When I let s go to infinity, I can take this A here also from f infinity, and then x infinity here. Yeah, or write like this. I can always replace the right hand side by expectation of x given f infinity over the set A, like so. And I have two random variables, this thing here and x infinity, which are f infinity measurable. A is also from f infinity by letting s go to infinity. And therefore, by the defining property of the conditional expectation, I find that x infinity must be the same as the conditional expectation of x given f infinity. Okay, then there's another thing here. The Martingale convergence theorem for backward martingales. Recall that a backward martingale is one where the time index is here on the negative natural numbers. And for those, there are extremely weak conditions for convergence. So the condition is here. This infinity must be bigger than minus infinity. For example, if I have a martingale, the expectation is constant anyway, so that's automatic. And then it tells me that I have almost sure and L1 convergence from xt to x minus infinity. And I can augment the martingale by this single point minus infinity. Okay, why is that? So first, if I have L1 convergence, I can write the following. Inf expectation of xt. Okay, it's a submartingale, but the time is in the negative numbers, which means if t goes to minus infinity, the expectation becomes smaller. But I have L1 convergence, which means that here must be expectation of x minus infinity, which must be bigger than minus infinity, because otherwise the L1 convergence would not hold. So that's easy. So that's the easy part. And the other part is the interesting bit. First of all, the almost sure convergence. That works as in the other result for the forwards martingales. But I have to exchange conditions here. The supremum over the expectation of xt minus must be finite. Exactly. Yeah, but this is the same thing as this here. So that property follows from this here. Yes, so I'm in the negative numbers. So the expectation of the plus thing here is growing because I have a submartingale, it's not decreasing. So the largest bit for the xt plus here is x0 plus, and that's finite anyway. And for the negative things here, I have to be a bit careful. But from the condition 2 here follows exactly what I need. By decomposing the xt here to xt plus and xt minus. And recall that xt minus is the negative part of xt, but so it's so recall that xt minus is defined by xt minimum 0 with a negative bit davon of this. So if xt is negative, then xt minus is positive, like this. And I can have yt, which is the expectation of xt minus 1 given ft minus 1. And that's not negative because I have a submartingale. So the expectation of the sum over the yt's, t from 0 to minus infinity, that's the expectation of x0 minus the infimum over all expectations of xt. And that's finite by assumption. Yeah, so this here is bigger than minus infinity. If we subtract it's smaller than infinity. So the sum over the yt's, that's a finite number. So this here is a non-negative random variable which with finite an expectation, so it's almost truly finite. And I can also say that the process AT, so AT is the sum over the ys, s from 1 to t, that's uniformly integrable because it is bounded by this non-negative integrable random variable. So it's uniformly integrable. And for mt, which is xt minus at, I have that must be uniformly integrable because it ends in m0, and all the others are just conditional expectations of m0. And we know that the conditional expectations, all conditional expectations of one integrable random variable, form a uniformly integrable random variable. So mt is uniformly integrable, at is uniformly integrable. So also xt must be uniformly integrable. And we are done because this implies here the L1 convergence. Okay. From this result, we can have a very nice proof of the law of large numbers. And it's the proof where we only have to assume L1 for all the random variables which we average over. And maybe you recall that this thing st here, we had that example, that one here, that is a backward martingale. You can maybe go back to the proof from the start of our martingale session. So that is a backward martingale. And since it's a martingale, the second condition here is fulfilled anyway, which means we have an almost dual and L1 convergence to this thing here, to some s minus infinity. Now the question is, what is s minus infinity? It should be the expectation of x1 if it's the law of large numbers, but you have to argue why that is. So s minus infinity is measurable with respect to some terminal sigma algebra here, so it must be almost truly constant. But st is a martingale, so including minus infinity, that must be a martingale, which means the expectation is constant. And the expectation is constant including at minus infinity. So s minus infinity must be its own expectation, which is the expectation of s minus 1. And s minus 1 is just the single random variable x1. So we have shown the law of large numbers here. And now I have two more results. One where we can, so the increasing process. So remember we had the increasing process for an L2 integrable martingale. So mt minus 1 must be bounded here. That's important. And if that's the case, okay, there's a null set, okay. But anytime the increasing process is finite, the martingale converges. And if it's infinite, then mt divided by the increasing process converges to 0. So why is that? Let's look at this briefly. Tk here is the stopping time where the increasing process exceeds small k. So the increasing process is finite. So if it's finite, let's say 10 or so, then T11 here is never reached, which is the reason for this equality here. If the increasing process is finite, sum of the stopping time here must be infinite. Therefore, okay, we know that m squared divided by the increasing process is a martingale. So the expectations are the same of m squared and the increasing process, like this here. Well, in this thing here, m at the time tk, okay, so there must be one jump above k here. The jump cannot be bigger than big K because of this assumption here, because one jump is at most K. That's the reason here for this K square. And before that, so before it jumped, it can at most have moved K. So that's this thing here. And for this reason, that's a submartingale. The expectation is bounded. So the limit must exist by the Martingale convergence result. Well, and the rest is easy because if I have this thing here, I can take one of the k's here where tk is infinity, and if I take one k where tk is infinity, this here converges to mt, to the limit of mt itself. That means tk is infinity, and mtk minimum t exists for some k large enough. That's the same as tk equals infinity, and this limit here exists. So you can forget about the stopping thing here. So that's for the first thing here, and for the second, I ask you to look at the manuscript. Okay, the last thing for today, the extension of the Borel-Cantelli lemma. You remember the Borel-Cantelli lemma? There we had events AT, and their probabilities were finite, for example. And then we said only finitely many of these A's occur. And that's here just another way of writing this. The sum of the indicators of AT, they are finite. And here it's a bit more refined. First of all, the A's, okay, they do not have to be independent. And if they're independent, I would just have the probabilities here. Then that would be the usual thing. But what I have to do, I have to sum the probability of AS given Fs minus 1. And if that's finite, then on this set here, on this set of omegas where this is finite, I have that only finitely many occur. For the reason of this, I have an application of the last slide. So MT here is a martingale, which is, well, the AS occurs, and I subtract the conditional probability. It holds that the quadratic variation at time t, well, as usual, I'm summing the increments square. And by this usual martingale trick, I subtract here the square of the both components. I mean, I would have the square, and then I can multiply it out, and xs is fs minus 1 measurable, and so on. Of course, the square of an indicator is the indicator. And the expectation of the indicator here, that's xs itself. So I have xs minus xx squared. And xs is fs minus 1 measurable, so I have this thing here. Again, that's of course bounded from above by ignoring the square part, so I have this thing here. So if the sum here is finite, I have that the quadratic variation is finite. And remember, when the quadratic variation is finite, this limit must exist. So we have this, a equals a with the intersection here. On m infinity finite, the limit exists. And what does it mean that the limit exists? It means that this sum here has to be finite. Otherwise it cannot exist, because the sum of this thing here is finite. So we have this, and we are done proving this extension of the Borel-Cantel lemma. Okay, that's it for today, and hope to see you next time.